Good day, folks. Welcome to Praise Mind Academy, where we bring brilliance to every lesson. In today's video, I want us to look at physical sciences, chemistry, paper 2. Okay, so this was written in 2025 November. All right, yes, let's dive into it. Now we start with multiple choice questions. They should be fairly easy to explain and move faster. Okay, yes. So the first one, it says, which one of the following name is a functional group of propan-1-ol? Propan-1-ol, it is an alcohol. So a functional group of an alcohol, it is a what? It is a hydroxyl group. Okay. Remember, alcohol has a functional group OH, which is a hydroxyl group. And then the organic compound C4 is converted to an alkane as shown in the reaction below. So this one takes place like that. From an alkene to an alkane, it means this is hydration, not hydration, sorry, hydrogenation. And hydrogenation reaction occurs in the presence of what? Of a suitable catalyst called what? PB, so platinum. Or it can be platinum, nickel, or palladium. Between the three. 1.3. Which one of the following statement always apply to compounds that are structural isomers of one another? Okay, that always apply to structural isomers. They belong to the same homologous series? No. Remember, for structural isomers, they can be functional isomers. They have different homologous series. They have same structural formula? No. They do not necessarily have the same structural formula. They have the same molecular formula. This is part of the definitions of what? This is part of definition of an isomer. Okay, an isomer, they have same molecular formula. So the answer for this one, it is A. And then 1.4, 1.4, by the way, the reason we are saying this one, they have the same structural formula, we can have the other one having a branch, the other one being a straight chain like that. And then can you see? The structure is not the same, but yeah, they are still what? They are still isomers of each other. And then 1.4, magnesium ribbon of mass 2 kg, 2 grams, react with excess hydrochloric acid of concentration this much. Okay, so excess hydrochloric acid of, let me try to zoom that, of 0.1 mole per decimeter cubed at 20 degrees Celsius. Okay, which one of the following will not increase the initial rate of the reaction? Let's now try to see which one will. Which one will? The ones that will, it is now using an increased temperature and increasing surface area, increasing concentration, as well as adding a catalyst. Okay, so now this will increase, this will affect, but if our options does not include these, it means it is the one that will not increase. Let's look at this one. Using 2 grams of powder magnesium, when you use powder instead of ribbon, when you use powder instead of ribbon, you are increasing the surface area. So this one will increase in the temperature. This will increase the initial rate. Using a longer piece of magnesium, this will increase now surface area. Also, surface area will increase. Therefore, when surface area increases, the rate will increase. Doubling the volume, well, volume has no effect here. So this one will be the correct answer thereof. 1.5, the following reaction reaches equilibrium in a closed container. Okay, so we have 1 mole of, remember, okay, 1 mole of gas in here. Okay, 1 mole of gas. So the gas, it is 1:1 because solid is not, okay, when we want number, we don't necessarily count for solid. Okay, then the reaction rate versus time graph for the reaction is given below. So we are given the the reaction occurs, it reaches equilibrium. This is equilibrium. And then, so let me do this. This is equilibrium. And then at T1, there is a disturbance. That disturbance can be now a catalyst because can you see both the forward and the reverse reaction are favored at the same time. Okay, so it can be an addition of a catalyst, and also since well the ratio is 1:1 here, it means when we increase the pressure, okay, when the pressure of the system increase, it will increase on both sides. Neither of the sides will be favored, or both of the sides will be favored, okay, equally so. So it can be a catalyst or now an increase in what? In pressure. Okay, an increase in pressure. So what changes made to the system at T1A? The pressure was increased, yes. This one is an option. The volume was increased, no. The temperature was increased, they told, okay, no. No, 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 no. More hydrogen was added, no. Okay, this is also a matter of knowing how to interpret your graph, knowing your graphs. A hypothetical endothermic reaction, you are told that it is an endothermic reaction. It is given below. So an endothermic reaction, it is that looks like this. Okay, okay, okay. And then we are told that the activation energy for the reverse reaction, it is 50. So the activation energy for the reverse reaction, it is 50. Okay, if it is 50, let me put it here and say, okay, no, it's fine. It's 50 kilojoules per watt. And then they ask us which one of the following is possible for the reaction above. Okay, so for the reaction above, this is the forward reaction. So which one is possible for the forward reaction? Now let's look. The heat of the reaction is 70 kg per mole. Can the heat be 70 kg per mole? Well, we don't know as of yet. We'll just see. It's possible though, it's possible. The activation energy for the forward is 50. No, the activation energy for the reverse is not equal to the activation energy of the forward. And the activation energy of the forward reaction, can you see that it is less than 50? So this one, no. The energy of the activated complex is 40. Well, if the energy of the activated complex it is 40 here, then it is nearly impossible for now to have an activation energy of 50 here. Sorry. From wherever here to have an activation energy of 50 there. That is merely impossible. Okay, so no, this one is not. So the activated complex, yes. No. And then the activation energy for the forward direction, it is 40. No. No. And then the one that is possible is this one, basically. The heat of the reaction is 70 kilogram, sorry, 70 kilojoule per mole. Okay? Yes. You can try to create a scenario here and maybe put, let's say here we have, I don't want to use numbers because they'll be silly, but it's fine. Let's just move on. 1.7. The products for the reaction between metal oxide and acid are what? We know that metal oxides plus acids form as what? Water and salt. You can make an example, by the way. You can say, let me take magnesium oxide plus let's say HCl maybe. It will form what? it will form as magnesium chloride plus H2O. Okay, so this, let's balance this like that. Okay, so this one is fine. So can you see it forms as magnesium chloride plus water? Magnesium chloride, it is a salt, by the way. The concentration of each of the four solutions, it is this much, so they have the same concentration. Okay, we have nitric acid, ammonia, sodium hydroxide, and bicarbonate of sodium. I don't know, what do you call this? Hydrogen carbonate or whatever. Which one of the following correctly places the solution in order of increasing pH? Of increasing pH. So I'll say if it is from increasing pH, it is from acid to base. So we know that NaOH has the strongest pH, okay? Has the, sorry, not strongest pH, has the highest pH value because it is the most basic solution among this one. And we know that nitric acid has a what? Less pH. This one has a high pH. So when we eliminate this one, no. This one is an option, but now the one with a lesser pH, it is now this one. Okay, so yes. So in choosing between A and B, the most correct one, it is B, because nitric acid HNO3, it is one of the strong acids that we have. All right. Alrighty. Let's move on to 1.9. A galvanic cell consists of the following half cells. So this is a cell notation. So this one moves from Fe3 plus to Fe2 plus. So in this one, so from Fe3 plus to Fe2 plus, the oxidation number decreased from 3 plus to 2 plus. This is reduction. In here, it means this is a cathode. Okay, but since when it moves from an, by the way, this is written in a bad way because it's supposed to be Fe3 plus in aqueous to Fe3 plus also in aqueous. So this does not necessarily, because this is a phase border, okay? Phase, when we do this line, we are showing that we are changing phase, but in this case, that's not the case. So you're gonna put a comma. I'm supposed to put a comma and then put a platinum or whatever inert what electrode. I need an electrode. Since well there is no electrode here. Remember, an electrode should be a solid. So since well there is no solid here to act as an electrode, so this will be my PT. I need a PT. Then this one will be from Ni2 plus to nickel. This is also reduction. Okay, this. Oh, okay. Let us do this. Let's not try to check between the two, between Fe and nickel, which one will undergo oxidation, because it seems like they did not give us in order. Let's try to look at that. Okay, I did not take my table of standard reduction table, but apart from that, this one, on this one, we will need PT as our inert electrode. Okay, so let's look at our options. Ni2 is reduced and Fe2 is oxidized, and then Ni2 is oxidized, and then Fe3 is reduced. PT is the electrode at the cathode. This one makes sense for me. Let me now try to fetch a reduction table so that it will make more sense. Okay, now I want us to look between Fe3 plus to that one and nickel, which one will undergo oxidization and which one. Now let's look. Now here we have those two. So let's see which one has a stronger. Okay, so the strength of oxidizing agent increases like this. So it means Fe3 plus, it is a stronger reducing agent. Okay, it is a stronger oxidizing agent than nickel. So it means Fe3 plus, since well it is a stronger oxidizing agent. Remember, when an oxidizing agent undergoes reduction, so this one will undergo reduction to form what? To form Fe2 plus. Okay. And by the way, when you use table 4C, I like to do it like this. So it means this one undergoes oxidization, this one undergoes reduction. Okay. So then nickel will be oxidized. Nickel will be oxidized to and nickel 2 plus. So now let's see our options again. Nickel will be oxidized, not Na2 plus. No, not this one. This will not be oxidized. Ni2 plus will not be reduced, but rather nickel will be. So this one, it's supposed to be written in this way. Supposed to be written that nickel is gonna be oxidized like that. Okay, so this will be my anode, and oxidization will take place in here. So none of these are correct. Ni is the electrode of the cathode. No, can you see this is an electrode of the anode? So this one is also incorrect. So the most correct answer is already indicated before that it's supposed to be what? Supposed to be number C. Hopefully that is clear. So the setup of an electroplating the setup for electroplating an iron metal with silver, it's very important that you highlight what we will be electroplating with is simplified here. So remember what we are forming. We are forming at the cathode. Okay? Remember, if this we are trying to electroplate the iron metal, it means this should be the cathode. Always we are forming at the cathode, then this should be an anode. And then at the anode, we should have whatever that we want to deposit in here. So it means we are supposed to have what? Silver. Okay? We are supposed to have what? Silver like that. We are supposed to have silver like that. Okay. No. In this case, it's supposed to be the silver in here. Okay, here we can say we have silver impurities. It's fine. And then the silver will undergo what? Silver will undergo reduction in here, oxidization in here to form like that, so that we take what? We take this Ag, and by the way, the anode is going to be positive, this one is negative, so that the Ag in here, it is deposited here so that it combines with what? With electrons. Can you see electrons? To form us what? To form us pure silver. So this is how we are going to electroplate this part thereof. So let's see. Which one of the following combination for the anode and reaction at the cathode is correct? Well, at the anode, we have what? A silver. We should have a silver rod here. Okay, they've already indicated, by the way. Anode. It was a matter of knowing which one is an anode. So we have a silver rod at the anode, and then the reaction that occurs there should have a silver. Okay, so this one is the correct, most correct answer, number D, the off. Okay, now let's move on to structured question 2. Now, question 2, nomenclature. Okay, it says the letters A to G in the table below represent organic compounds. Okay, now let me do this. We have here what it is. What this is a ketone. How do I know it is a ketone? It has a double bond or at the between carbons. Okay, so this is gonna be my ketone. Okay, and remember, ketone, it is a functional isomer of a aldehyde. All right, and then this is what? This is haloalkane. This is haloalkane with that particular name we will see. And then we have CH3CH. and then a branch CH2, CH double bond O. Okay, here we have an aldehyde here. I want to draw a structure so that you see. It's gonna be CH3, CH, and then a branch here, and then we have CH2, we have C double bond O H. So this is an aldehyde. Okay, and since well it has how many? 1, 2, 3, 4, and 5. Since well this is an aldehyde that has 5 carbons as well as A and C are now functional isomers. A and C are functional isomers. Remember, ketone and aldehyde are functional isomers only and only if they have the same molecular formula. In this case, they have 5 carbons and whatever oxygen, hydrogens plus 1 oxygen. So these are functional isomers. And then we have C4H10O. This is my alcohol. I can show you this is an alcohol. 1, 2, 3, 4, 5, 6, 7, 8, 9, oxygen 10. Okay, 10. So yes, this is my alcohol. Pentane, it is pentane. Pent means 5. 1, 2, 3, 4, 5 carbons. This is an alkane. Just an alkane. C3H8, this is also an alkane, but in this case it is propane. Also an alkane called propane. And then here we have what? We have a double bond. We have an alkene here with whatever special name that we will see later on. Okay. But this one we can now name because we start from here. You're going to be 1, 2, 3, 4, 5, 6. If I went here, it's going to be 4 and 5. So no. So it is 1, 2, 3, 4, 5, 6. And then I encountered a branch, and a methyl branch. Also here an ethyl branch because it has 2. This is an ethyl branch. This is a methyl branch. Okay. So if I were to name this, I'd say it is, remember eth comes before meth, E comes before M. So it's going to be at carbon number 3, I met let me do this. At carbon number 3, I met an ethyl. And then on carbon number 2, I met a methyl. And then I have longest chain, which is hex. And then on position number 2, I had a what? Can you see it is between 2 and the functional group, it is between 2 and 3. So I'm going to take the smallest one, which is 2. I made an what in functional group of alkene, which is in. So this is the name of that particular compound thereof. Okay, now let's answer the question. The answers should be fairly easy as we move now. The letters, write down the letters that represent each of the following. An alcohol. An alcohol, we said an alcohol, it is number D. D, it is an alcohol. 2 compounds that are functional isomers of one another. Functional isomers, remember I said functional isomers are what? A and C. Okay, A and C. A and C, I'm going to write it here, A and C. 2 compounds that belong to the same homologous series. Same homologous series, E and F. Can you see alkane? Also, this one it is an alkane. So homologous series, they are both under alkanes. Okay, yes. Homologous series, it is E and F. E and F. Alrighty. Now, write down the IUPAC name of compound A. Now, let's go to compound A. We can now erase this. We are done analyzing compound A. How can I name compound A? I'm going to start naming from here. Actually, let me do this. It's going to be 1, 2, 3. If I go down and say 4, it's still fine. Or I can use the longest chain 4, like that. So when I do that, I see that on carbon number 3, I have a methyl group. Okay, I have a methyl group. Remember one branch, when we have a branch with one carbon, it is a methyl. Okay, this is a methyl group. And then on carbon number 2, okay, well, this is a ketone. Okay, this is a ketone on carbon number 2. It shows us this is a ketone. And then the name will be now 3-methyl. On carbon number 3, I made a methyl. And then the longest chain, it is butane. And then on carbon number 2, I have a ketone there. Okay, I have an ending of 2-ol. Okay, yes. So the name for this one is supposed to be something like 3-methyl butane. Okay. On position number 2, I made a what? A ketone. Butane 2-O. Okay. IUPAC name of B. IUPAC name of B. Now I'll start naming from either here or this side. So let me see this side. This side is going to be 1, 2, 3, 4, 5, 6. Okay. Or if I do not take 6 here, I can say this is 6 and 7. Now the longest chain is 7. So I'm going to say here, this is my methyl group. This is my methyl group. Also, this is a methyl group. Remember, methyl group, it is a branch, by the way. And then on carbon number 2, I have a Cl. And then on carbon number 6, I have a Cl. So let's name from there. When we name from there, it's going to be, we have on carbon number 2 and carbon number 5, we have methyls. Okay, so we have 2.5 dimethyl. Okay, 2.5 dimethyl. Okay, but also on carbon number 2 and carbon number 6, we have chloro. Is this chlorophyll? Chlorine. So we have chlorine on carbon number 2 and number 6. So when we name, we know that chlorine, which is going to be chloro, comes before methyl. But since when we have 2 of these, we're going to say di. We have 2 of these, dichloro, dimethyl. So we're going to start with dichloro. So we're going to say it is on carbon number 2 and 6. Sorry, on carbon number 2 and 6, we made a 2 chloros. Okay, so hence we say dichloro. And then between a number and a letter, should be a hyphen there. Between a number and a number, there should be a comma. And then we also made on carbon number 2 and 5, we had methyl, but there were 2 of them. Do not mix a dimethyl as well as ethyl. Ethyl, it is when we have a branch that has 2 carbons. A branch that has 2 carbons. But dimethyl means 2 methyls. Okay, yes. Then the longest chain, it is 7. 7, it is heptane. So I cannot use a hyphen there. Heptane. Now, let's say now one decided to name from here. What would have happened if one decided to name from here? Let's say this is 1, 2, 3, 4, 5, 6, 7. So we'll still have a branch, okay? But now our branches will now be on, okay, let's start with our chloro. So our chloro will be on carbon number 2 and carbon number 6. So we will have 2 and 6, okay? 2 and 6 dichloro. So the 2 and 6 dichloro is still the same. So let me write this hand. So we will have had 2.6 dichloro. That one did not change. But now let's look at the branch are now in carbon number one. The branch, it is now in number 3 in black, number 3, as well as number 6. So it is now 3,6. So now our branch is now 3,6. So 3,6 dimethyl heptane. And by the way, when you name a haloalkane, you do not prioritize a branch or a haloalkane. or an alkane, sorry, a halogen, what you do, you check the one that yields to a smallest number. Okay, so let's see why the one in red it is incorrect. The number here it is 8, 2 plus 6 it is 8, and then 2 plus this it is 7. So the total number it is 8 plus 7, which is 15. And then here we have 2 plus 6, it is 8. And then 3 plus 6, it is 9. The total number here, it gives us 17. So the one with the smallest one, it is this one. Hence, the blue one, it is the most correct, the correct answer. I hope it makes sense. I hope it makes sense. Now, IUPAC name of G. Okay, I think we have already named that to be 3-ethyl, 2-methyl, hex, 2. Now, can you see this? We have a branch that has 2. This is ethyl. This is not dimethyl, okay? 3-ethyl, 2-methyl. Let's name that. 3-ethyl, 3-ethyl, 2-methyl. Can you see between a number and letters, there is a hyphen? 3-ethyl, 2-methyl, hex. This, you cannot say hexane because this is an alkane, alkyne. So they are just alkene. So it's going to be hex. And then position number of the alkene. Position number of the alkene, it is number 2. Hex, just hex. And then 2 in. Okay, good. Now they want us to draw now structural formulas. Okay, structural formulas of 2 straight chain positional isomers of D. Okay, positional isomers of D. It tells you that we will have same chain but different. Can you see straight chain? So it should be just straight, no branch. Let me say no branch. Also different position of OH group. Now remember D, it is an alcohol. Remember D, it is an alcohol. So it has an OH. So how can I draw those structural isomers? Positional isomers. I'll say the first one can look like this. The first one can look like this, where we have H, C, H. Okay, let me, so that they will have enough space. H, C, H, H, like that. How many carbons does it have? It has 4 carbons. Again, yes, it has 4 carbons. So I'm gonna say like that, and then or I can say this is my, okay, this is the first one. Now, can you see now the position here? The position of the functional group, it is on carbon number 1. Okay. Now, the second one, we just change the position. We take the position and we just take it to position number 2. It's fine. This is what we were required to do. You take the position to just number, okay, number 2. Let's take OH to this position here. And then have H, H, H. Can you see now the position? The position. This is in position number 1. This is in position number 2. Hence, now we have what? Positional isomers. And by the way, they are straight chains. The chain is straight. Okay. We have a straight chain, no branching. Okay. So that you have one independent factor, which is now a position. Okay. Type of isomerism, which is a positional isomer. Okay. And this, you can name it, if you're interested in the name of this can be named butan 1-ol, because it is butanol, but having an alcohol in position number 1 or OH in position number 1. This one can be butan 2-ol, in case you're interested in their name. Okay. 2.3, compound E. Compound E reacts with oxygen. Remember, oxygen should be in excess. Okay. Okay, according to the balanced reaction. So this is a combustion reaction, by the way. And for the combustion reaction, oxygen should be in excess. Okay, remember the combustion reaction, it says it is the burning of alkanes in the presence of excess oxygen. So oxygen should be in excess. So now they tell us that initially 8 grams of compound E and initially 8 centimeter cubed of compound E and 50 centimeter cubed of oxygen were injected into the container of an adjustable volume and allowed to react. Okay, so they ask us here what type, write down the name for this reaction. So we know this is a combustion reaction. This is a combustion reaction. And then they say calculate the total volume of the gases present in the container. So the volume present in the container is going to be the volume that is produced from CO2 as well as H2O, because now as the reaction occurs, we're going to form CO2 and H2O plus the volume of the one that is in excess, which is what? Which one is in excess? Which is O2. Okay, so how can we do the steps here? How can we go about those steps there? What we will do, we will say, okay, we will say we know that CH3H8 is it CH3? Yeah, not CH3, C3, sorry, is a limiting reagent. Let me say reactant, however the English there. So it means now we will use the 8 grams for that one to see how others reacted, okay? So now, let's now say, let's use the ratio between, okay, first one, let's use the ratio between CH3 and O2. So the ratio between CH3 and O2, it is 1:5, okay? 1:5. But we know that all of the 8 centimeter cubed of C3H8 will fully react. Why? Remember, it is a limiting reagent. So we're going to say we know that 8 centimeter cubes of this one will react. So how much of O2, volume of O2 that reacted, basically? The one that reacted, remember O2 is a reactant. So the volume of O2 that reacted is going to be 5 times 8, which is 40 centimeter cubed. But now, if 40 centimeter cubed of O2 reacted and initially we had 50 centimeter cubed, so it means the volume of O2 that is left or that is in excess is going to be 50 minus 10, which, sorry, 50 minus 40, which is 10 centimeter cubed. And then now let's try to see the volume that is formed. Okay, the volume that is formed is going to be between CH3 as well as carbon dioxide. Now the mole ratio between CH3 and carbon dioxide, it is 1:3. We already know that 8 centimeter cubed of this will react. We want to know the volume of CO2. This is not reacted, this will be the one that is formed. So when we find volume of CO2 that is formed, we realize that it is 8 times 3, which is just 24 centimeter cubed. And then let's do the same also for, what is this? Let me do this. Let's do the same also for H2O. So between CH3 and H2O, the mole ratio is 1:4. 1:4. Therefore, we have 8 centimeter cubed here and then we want to volume of water that is formed. Okay, then the volume of water that is formed there or produced, it is now 4 times 8, which is 32. And then if that's the case, it means now total volume present in the container at the end of the reaction will be now, remember, the volume produced or formed plus the volume that it is in excess. So the volume produced is going to be 32 centimeter cubed from H2O plus 24 centimeter cubed from CO2 there. Okay, it's going to be this one plus the 10 centimeter cubed that is left from the oxygen there off. Therefore, when I do mathematics, it gives me something like 66 centimeter cubed, or someone might write it as 0.66 decimeter cubed. It's fine. So this is how we will have went about that one. Okay, so it was a nice question 2 there off. Now let's go to question 3. Okay, question 3. If physical properties, it says now two bottles contain compound A and B with the same molecular formula. Same molecular formula. So we know the ones that have a molecular formula that has O2. This has a general formula of CnH2nO2. And this is a general formula of esters as well as carboxylic acid. Okay, so between A and B, we have ester, the other one is carboxylic acid, okay? And remember, ester has dipole forces. This one has hydrogen bonding. So it means this one has a higher boiling point than this one. Okay, let me remove this. We know this one is the strongest, so it will have a higher boiling point. So they say the boiling point are used to distinguish between the two compounds. Yes, boiling point will tell us, because now the one with the highest boiling point will be carboxylic acid compared to an ester. Okay, define the term homologous series. So homologous series, you can define it as a series of organic compounds that can be described rather by the same general formula and have the same functional group. Or someone might say a series of organic compounds in which one member differs from the next with a CH2 group, however you define that one. Know all your definitions. Identify the two homologous series to which these compounds belong to. We have already indicated that carboxylic acid, also esters. Okay, so now they tell us that the following are the vapor pressure of the compounds at a given temperature. Compound A, compound B. Remember, the higher the vapor pressure, the lower the boiling point. Or the lower the vapor pressure, the higher the boiling point. So in this case, compound A has 0.071 kPa and compound B has this one. So can you see that this one has the lowest vapor pressure? So if this has the lowest vapor pressure, it means it has the highest boiling point. So this one, compound A, fits now to be, if it has the highest boiling point, this one fits to be a carboxylic acid, then this one will be an ester. Okay, yes. So if A is a carboxylic acid, now it's fine. Now, write down the structural formula. How can I write down the structural formula of compound A? Compound A, I now know it is a what? It is a carboxylic acid. So a carboxylic acid with 4 hydrogens is going to be 1, 2, 3, 4, like this. Remember that how do I see a carboxylic acid? I see a carboxylic acid by double bond OH. This tells me that this is a what? This is a carboxylic acid. A Q. Okay, at the end. A Q at the end. Okay, now this is what I refer to as a carboxylic acid with 4 hydrogens. And you can count with 4 carbons, sorry. You can count if now the hydrogens are the same. 1, 2, 3, 4, 5, 6, 7, 8. Yes. Oxygens, there are 2 of them. Then the IUPAC name of actually, let's say IUPAC name for a possible compound B. Compound B, it is just an ester with 4 carbons. So an ester with 4 carbons can now be named like this. It can have 1 carbon from the alcohol. Remember, when you name an ester, it is apart from an alcohol plus apart from a carboxylic acid. So this is going to be something, alcohol is going to be something aryl, and then something from a carboxylic acid O8. Okay, let's say if we have 1 alcohol, it's going to be methyl and then 3 propanoate. So the first option that you might have, it is methyl propanoate, or I can have, if I have 2 alcohol and 2 carboxylic acid, it's going to be ethanoate, or if I have 3 alcohol, it's going to be propyl. Let me do the or with the different color. Or I can have 3 carbons from alcohol, that makes it propyl, then methanoate. So these are the possible names, because either way they have what? They have 4 carbons. Okay, they have 4 carbons. Even if you were to draw the structure thereof, it will have 4 carbons as well as 8 oxygens. Hope it makes sense. 3.4, write down the strongest van der Waals forces between molecules in compound A. Compound A is the carboxylic acid, so the strongest forces there are hydrogen bonding. The strongest hydrogen bonding. Remember, carboxylic acid, in addition of hydrogen bonding, it has dipole as well as London forces. Compound B, in addition of London forces, it has what? The strongest, which are dipole forces. Okay. And then they say to you, which compound A or B has a higher boiling point? Well, it is A. But now they say, give a reason for the answer by referring to the strength of intermolecular forces. So we know that hydrogen bonding of compound A are stronger than dipole forces of compound B. Okay. Then now the boiling point of compound A is measured again on another day when the atmospheric pressure is much lower. Okay, how will the boiling point of this compound now be affected? How will the boiling point of this compound now be affected? Choose from increase, decrease, or remain the same. Now, first thing first, note the definition of a temperature, so of a boiling point. What is a boiling point? The boiling point is temperature at which the vapor pressure equals, okay, the atmospheric pressure. So now they are telling you that the atmospheric pressure on that particular day, it was low. So if there is a lower atmospheric pressure, it means there will be lower vapor pressure. Okay, there will be the vapor needed. Okay, the vapor that we need to boil, vapor needed to boil compound. There will be less vapor needed to boil the compound, and therefore, if there is less vapor, it means now the boiling point will be low. Okay, therefore there will be low boiling point. Boiling point. I hope it makes sense. So now we can choose confidently our answer and say the answer here it is what? The answer here it is decreases. It's gonna decrease. Okay, good. That was a good question. Question 3. Question 4. Study the 3 organic reactions 1, 2, and 3, or Roman figure number 1, number 2, number 3, respectively below. Compound T and W are organic compounds, R and S are inorganic compounds. Okay, consider only major products. Okay, HBr plus something to W. This has a possibility of being an alkene forming an haloalkane. By looking at this, okay, because they are adding HBr, and it's not a substitution reaction to show that we only form one product. So it shows that the product that is formed here, all of these reactants now were all inserted on T. So now hence I'm convinced that this is a addition reaction. Addition reaction, okay? Or hydrohalogenation. And then W, when added with sodium hydroxide, it is now substituted with OH. So can you see now, this will be a substitution reaction. Why? Because the haloalkane thereof that we had in W was substituted with an OH to form now CH3, CHOH, CH2, to form an alcohol. And we know that haloalkane reacting with a dilute strong base, okay? Dilute strong base, which is dilute sodium hydroxide, it forms as alcohol plus R. R should be now sodium. The sodium here will react with what? With the halogen, because they substituted OH with a halogen. So the halogen was what? Was Br. So this is going to be sodium Br. And now I now know the haloalkane that is going to be formed here. So the haloalkane that is going to be formed is going to be CH3 CH Br. So instead of Br, can you see now they were substituted with OH? So in place of OH, it means there was a Br there. And then CH2 CH3. Therefore, I'm now convinced that the alkene here was between here. Okay. So it was going to be CH3, CH, when we take the Br that we added here and the hydrogen that we added there. So it's going to be CH, CH, and then CH3. I'm not sure if that's feasible, but let me do it like this. CH3, CH, CH, CH3. This is now the T. I'm convinced now. Okay. And then see this one now, our alcohol undergoes whatever, and then it forms T plus water. So this is dehydration. And dehydration occurs in the presence of H2SO4, concentrated H2SO4. And then T will be now an elimination. We eliminated OH as well as H. as well as H somewhere. So it means we're gonna form back what? We're gonna form back what? This part again. We're gonna go back to alkene T. Oh, by the way, they told you. Okay, so we're gonna go back to alkene T. Okay. I think us doing this, we are done. We have answered almost every question. This is elimination, by the way, or specifically dehydration, because we are removing water. This one, it is the type of additional reaction which we might refer to as uh, hydrohalogenation. We are adding hydrogen as well as halogen. This type of substitution reaction, it is what? No name. Okay, now IUPAC name of W. IUPAC name of W. IUPAC name of W. So can you see in WFCH3CHBr, blah, 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 blah. So the IUPAC name of W is going to be on position number 2. We had an OH, but originally on position number 2, we had a what? We had a Br. So it means on position number 2, we have a bromo. So I can say we have 2 bromo, okay? 2 bromo, and then the longest chain it is 4, butyl. 2 bromo butane. 2 bromo butane. So that's the name of that. Sorry, there is no hyphen between bromo and butane. These are numbers. Sorry, letters. So it is 2 bromo butane. And then name of formula R. Name of formula R. This is sodium, and then with that Br. So it's going to be sodium bromide. So someone might say sodium bromide. Or by its formula, it is sodium bromide. Name 2 types of reaction. Name two names for the type of reaction in reaction 1. So first thing first, in reaction 1, we know that it is what? It is an addition reaction. So you can say this is an addition reaction, or you can call it specifically by its name, which is hydrogen plus halogenation. Hydrohalogenation, like that. Let me write that, hydrohalogenation. Name of formula of S, So I said the name, it is concentrated, which we don't need in this case, sulfuric acid. Or one might say it is just H2SO4. Then write down the structural formula of compound T. Compound T, it is now an alkene. Okay, an alkene. Now I want you to know Markovnikov's rule. Richer gets richer, poorer gets poorer, and Zayev's rule. Now, if we had something like this, Br, hydrogen, 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 hydrogen. Can you see that here? When we eliminate, again now they added HBr to form this one. When we eliminate now Br to go back to what we had initially, you're going to take Br here, and then where you have already taken, you can't take again. So now we need to take hydrogen. Where should we take hydrogen? Zayev's rule and Markovnikov says now you take from the one that is already poor. The one that has the smallest number of hydrogen, you take from it. This one has 3 hydrogens. This one has 3 hydrogens. But this one has 2 hydrogens. So I'm going to take the width from the one that has least hydrogens. Which one is that? Is this one. So I'm going to take hydrogen from this one. And when I do that, can you see now I'm removing these? But now as I remove those, I will now have to add a bond between the ones that I removed. Which one? These. I need to add a bond here and then remove this. So this is how the structure is going to look like. But let's now try to draw that beautifully off. I wanted to explain how we find that structure, by the way. So it's going to be H like that, yes, double bond, yes, H, like that, like that, and like that. By the way, just make sure that you count the number of bonds. It is 1, 2, 3, 4. For this carbon, fine. For this carbon, it is 1, 2, 3, 4. Then they are fine. Remember, carbon can acquire at most 4 bonds. Compound W can be converted to P in one step. Compound W, this one, it can be converted to T in one step. So how can I move from haloalkane to alkene? Remember, this is a haloalkane. This is an alkene. How do I move from haloalkane to alkene? For me to move from haloalkane to alkene, I need an elimination reaction that is called dehydrohalogenation. I'm removing the hydrogen as well as halogen. So, and now the reaction condition for that one, the reaction condition for dehydrohalogenation from D to T, that is dehydrohalogenation, dehydrohalogenation. So D means we are eliminating. And for the reaction condition of this one, it is strong heat plus concentrated strong base. Okay, and now the question is, state besides heat one other reaction condition for this reaction besides heat, because they know heat, you cram it all here. So it's supposed to be what? Concentrated, very important, concentrated, very important, strong base. Or you can say strong base, lithium hydroxide, potassium hydroxide, whichever strong base. Why are we saying concentrated? Because for this one here, can you see it also uses sodium hydroxide, but it is a substitution reaction. But this one, it uses a what? It uses a dilute strong base. Okay. Now, we move to 4.2. A compound with a formula C10H22 undergoes a cracking reaction according to the reaction like that. So we know now for us to balance this. So if there are 10 here and 22, here we have 4. So it means for us to balance on this side, we will need 6 hydrogens, and as well as if we already, so 6 carbons, and how many hydrogens on this side? 12. Okay, but already there is a 2. There is a 2 as a factor here. So this can be written as 2. When we take 2 as a coefficient, it means it's going to be C3 and then H6. Okay, so X, it is this. Okay, and this is an alkene. This is an alkene with a name propene. And then they now, okay, they tell us that the mixture of the two product is bubbled in bromine water in a darkened room. Okay. So 4.2.2 says state one. Okay, so 4.2.1 define the term cracking. The term cracking refers to the chemical process in which longer chain hydrocarbon molecule are broken down to smaller, more useful molecules thereof. Okay. Then 4.2.2 says state one change besides a change in temperature that will be observed when the mixture is bubbled in bromine water. We know that the bromine water will get decolorized. Okay. We say the bromine water will decolorize. Okay. Br water, Br water will decolorize. Okay. This is the observation that we get thereof. Then the structural formula of X. Okay, we just said X. X should be an alkene. Let me say C3H6. So, which is an alkene. So you can draw a structure like this. Okay. So you can draw a structure like this as long as it is an alkene. Okay, whether this one is on this position on the other side, it's fine. Just know that it should be an alkene with three carbons like that. And then 4.2.4 says which compound X or C4H10 reacts faster in bromine water? Well, the one that reacts faster, it is X. X. Why? 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 It is because, let me say X. Why? X has double bond. Which readily undergoes an addition reaction. Okay? In the presence, very important, in the presence, absence rather. It does not need UV light. Whereas now C4H10 needs UV light, needs UV light to undergo substitution. Substitution. So in particular, in the absence of UV light, X is faster than C4H10. So it means in the presence of UV light, X will be more faster. Okay, since well it does not need UV light, it means when there is UV light, then it means now the reaction will now be more faster. Okay, yes, this one is for this one it is a spontaneous reaction. Okay, X undergoes spontaneous reaction. It does not need to be induced. Okay, so yes, that's that, guys. Beautiful stuff. All right. So now let's go to question 5. Rate of reaction. Define question 5. Define the term reaction rate. Okay, so we know reaction rate. It is the change in concentration of uh, of reactants or products. Very important per unit time. Very, very important that you include that per unit time. This is a two or nothing, by the way. Did I get it correct or incorrect? Did I get it correct or incorrect? Two or nothing. 5.2, carbon monoxide react with oxygen to form carbon dioxide in the sealed container like that. So here's the balanced reaction. Then the graph below shows the concentration of O2 versus time. Okay, so the initial concentration here, if my reading is correct, I see that the initial reading here is 0.27. And then at 10 here, it is just this one. Okay, it is 0.15. And then, yeah. At which time, 10 seconds or 30 seconds is the reaction rate faster? Well, it is the reaction rate, it is faster when the reaction just starts. Okay, when the reaction starts, the gradient is steeper. Can you see? Compared to 30, can you see during 30? Now the gradient now starts to become gradual. Okay, so for this one, the gradient it is steeper for the first 10 seconds, but now as it goes, it becomes gradual until now it becomes now until the reaction become complete, basically. So here it is faster, and then here it is slower. Okay, so at which time is the reaction rate faster? When time it is 10 seconds, okay? When at time t seconds, at time t is equal to 10 seconds. And then 5.2.2 it says the reaction takes place in a 3 decimeter cubed container. Calculate the average rate in what? Mole per decimeter cubed, at which carbon dioxide is formed in the first 10 seconds. So at which carbon dioxide is formed. But here we have a graph of oxygen. So since well they want it in number in moles per second, it means now we need to find number of moles of carbon dioxide. But how can we find those? We can use now the O2 that we see here. Okay, the O2 that we see here to convert to number of moles. So I can say number of moles of O2 it is equal to CV. Very important that for the 10 seconds, okay? For the 10 seconds. So number of moles of O2 is gonna be CV. Remember, C is equal to N over V, and then number of moles is equal to CV. And then the concentration, how much is the concentration? Let's now analyze the graph. The concentration now changes from at 10 seconds. Can you see at 10 seconds now the concentration it is 0.15 and initially it was 0.27. Okay, so concentration you can say it changed from if you want to show very well, it moved from 0.27 to 0.15. Okay, and then you need to multiply by the volume. The volume it is 3 decimeter cubed. 3 decimeter cubed. So you get that the change or the number of moles of O2 there it is 0.36 moles. And then the ratio between oxygen, the ratio between oxygen and carbon dioxide it is 1:2. So it means for every 1 mole of oxygen there are 2 moles of carbon dioxide formed. So it means number of moles of CO2 for every 1 mole of these, okay, there are 2. Okay, let me say it's going to be double number of moles of O2, which is just 2 multiplied by 0.36, which is 0.72 moles. Remember, when you use mole ratio, guys, you can confirm CO2 to O2. The ratio is 1. Okay, CO2 it is 2:1, and then we have this to be 0.36. If I want this, then when I solve for n, it's going to be 0.36 multiplied by 2. Hence, I did that. And then now, but the question was, let's want the rate. What is the rate? So the rate is going to be now change in number of moles because it is in mole divided by time. And the change in number of moles is going to be 0.72 minus 0. I like to put minus 0 because it is a change. And then it's going to be the time, it is 10 seconds minus 0. And then the rate now that we get it is 0.072 mole per second as per required. Okay, good. Which reactant is in excess? Which reactant is in excess? Can we see that O2 here? O2 here becomes complete. Okay, goes to equilibrium, reaches equilibrium, or now its reactant are finished here. Can you see from this portion here, its concentration no longer changes from, I can say, approximately 52 all the way here. Now, the gradient does not change. So it tells you that it reaches completion, okay? It reaches completion. So it means O2 is a limiting reagent. So if O2 is a limiting reagent, it means the one that reacts with it is going to be the one that is in excess. So CO is the what? Limiting, it is the one that is in excess. Okay. The reaction was repeated using a smaller sealed container. How will this affect the magnitude of the gradient of the graph at the beginning of the reaction? Now they are using a smaller sealed container. They are decreasing the volume. Okay? They are decreasing what? Decreasing my volume. Then the question is, how will this affect the gradient of the graph at the beginning of the reaction? Well, the gradient of the graph will decrease because now, when I decrease the volume, I'm lying, it's going to increase. I want you to see this. According to this formula, C is equal to N divided by V. Okay? Sorry. Provided that the number of moles are constant. Okay, the number of moles are constant. They did not add any number of moles. They did not add any gas, any nothing. If this one decrease, can you see that concentration is inversely proportional to the volume? It means now concentration will increase. And now take concentration as the collisions. Okay, now when the volume is now, we have a smaller volume. Now it's like having a balloon. Yeah? When you're having a balloon and then you try to compress it, when you compress that balloon, you are using what you are doing, what you are decreasing the volume. And what happens to the particles? Your particles now collide frequently. So you are making them to be concentrated at one place. Okay. So when they become more concentrated at one place, sometimes you get to know that your balloon burst. Okay. So it's why? It's because now it is too concentrated on one place, and now there are frequent collisions that occurs. Okay. So you can say why? Because there will be an increase in concentration. In concentration of O2 or concentration of the reactants. Therefore, you know that when the concentration, by the way, this is concentration. This is concentration, guys. This bracket means concentration. So when there is an increase in concentration, you know there is what? More effective collisions, okay? There will be more effective collisions, even though you're not required to come here. What you're supposed to know is that there will be an increase in concentration when you decrease the volume. Okay, yes. So it will increase. And then the reaction between sulfur dioxide and oxygen takes place in a sealed container according to the balanced equation below. So the reaction, it is exothermic. So remember, this one tells us about the forward reaction. So it tells us the forward reaction, it is exothermic. Why? Because change in H is less than 0. And I know exothermic reaction, it is a reaction that releases heat. So it means the reverse reaction is going to be endothermic, with change in H being equal greater than 0. And then we know that for endothermic reaction, it is the one that absorbs heat. Okay. And by the way, if for the reverse reaction, the change in H it is negative 196, it means also if for the forward reaction it is negative 196, it means for the reverse it is positive 196, and so it is endothermic. By the way, change in H does not change. Change in H does not change. Temperature can increase and remain or decrease and what, but the change in H does not it does not change. Then the question is, was there a net release or net absorption energy during, very important, they highlighted this, during the reverse reaction? So can you see that the reverse reaction, it is endothermic, since well the forward reaction, it is exo. So we know for the reverse reaction, which is endo, there will be a net absorption. net absorption. Define the term activated complex, which is now the unstable transition state from reactants to products. Just know your definition. This is what we refer to as the activated complex. And then we are told that 5.3.3, a catalyst, which is now a vanadium pentoxide, okay, vanadium pentoxide is added to the reaction, okay. Explain in terms of collision theory why the rate of the reaction will increase. Now, this you should know off by heart is that the catalyst provides a path of lower activation energy, okay. Remember, it lowers the what? Lowers the activation energy. Very important. Lowers the activation energy. And then when the activation energy is now low, when let's say we have a graph like this. When the activation energy is now low, like this. Can you see now? It means now more particles will be able to reach this spot. If we are having particles that are fighting here, there will be more particles that will reach this spot than this spot. Or we can use Maxwell distributive curve, Maxwell-Boltzmann distributive curve to show that if I had a graph like this, and let's say this is my EA, and then shift my EA here. When I shift my new EA here, can you see that instead of having these particles now being sufficient, we will now have these. So another thing is that the more particles will have sufficient kinetic energy, okay? So you can say sufficient energy that is greater or equal to the activation energy. And then if that's the case, therefore, there will be more effective collision that will take place per unit time, okay? Per unit time. And then you know that the reaction rate will increase, but already they have told you that the reaction rate will increase. You are just reasoning. Okay, curve X is the Maxwell-Boltzmann distributive curve for the reaction above. Okay, so more SO2 is now added. More SO2 is now added to the container. When SO2 is added to the container, where's SO2? When SO2 is added to the container, we know there will be an increase, okay? When we increase this, the Chatelier will say, okay, we don't want more of this. We will now try to transfer some of them to that side so that we balance out. And then when we transfer, this one will decrease, and then this one will increase. And now, since we are favoring the forward reaction, therefore it means exothermic reaction is favored. Okay? Exothermic reaction is favored. And then the temperature, can you see I'm saying the temperature of the reaction will increase. The temperature of the reaction will increase, and SO2 will decrease, O2 will also decrease, SO3 will increase. But now the question is, how will this affect the heat of the reaction? Heat of the reaction, it is this. Okay, this is the heat of the reaction, change in H. Now, remember we are given that the heat of the reaction, it is this one. Now, the heat of the reaction remains unchanged whether the forward or reverse reaction is favored. So the answer is remains the same. I'll explain this. It's confusing. People will say increase because we are favoring the forward reaction, and forward reaction, it is exothermic, and exothermic reaction releases energy. But in this case, they are not asking us about the temperature. Okay? Let me note this. Heat of the reaction is not equal to the temperature, or is not even equivalent to the temperature. So the heat of the reaction, it is just changing H. Okay, changing H does not depend on the only Chatelier and the shifting of the equilibrium and all of that. All it depends on the kinetic energy, on the reactants that react thereof. Okay, on the reactants that react, and yes, only. The only time we can affect the heat, it is when we change the reactants. Okay, so now this I want to believe makes sense. Heat of the reaction, not the temperature. Redraw the graph in the answer book on the same set of axes. Draw the curve that will now be obtained when SO2 is added. When SO2 is added, it means we will have more particles. When we have more particles, it means now, by the way, the peak will be the same. At whatever the energy, we will have the same peak, but now at a higher thingy. Also, let's say we had an activation energy here. If we had an activation energy, can you see that initially only these had now sufficient kinetic energy that is greater or equal to the activation energy? But when we increase more particles, it means now more particles will now be able to have sufficient kinetic energy. These ones are particles with sufficient kinetic energy. That is greater or equal to activation energy. But since well, they did not want us to draw it, it's fine. We don't need that. Okay, so yes. By the way, it should be under the same peak, should be under the same temperature. Because the minute you shift it like this, if it were to be like this, let me show you. If it were to be like this will be now temperature. Or if it were to be like that, this will now be temperature, because the curve now, the peak here, should be under the same kinetic energy. We are just increasing the number of particles, nothing much. Apart from that, everything will be the same. Okay, and then let's label this to be now Y. So that was that for question 5. It was very beautiful. Let's move on to question 6, chemical equilibrium. Chemical equilibrium. Question 6. It says equilibrium is established at 25 degrees Celsius in a saturated calcium hydroxide solution to form now calcium ions as well as 2 moles of hydroxide ions. State Chatelier's principle. Chatelier's principle says now, when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. By the way, closed system not isolated system. Closed system correct, isolated system wrong. We use isolated system in physics. In chemistry, we use a closed physics. So, sorry, a closed system. Okay, yes. Okay, now we are told that 6.1.2, a few drops of concentrated HCl are added to the equilibrium mixture. What effect does this have on the mass of CaOH? When we add HCl, remember this is a ion effect reaction. So remember HCl has H plus and Cl minus. Well, Cl minus are just spectator ions, okay? So the H plus here, the H plus will be the one that takes place in the reaction. Now, when the H plus now comes into effect, it's going to now react with what? With OH, because it is the one with the minus charge and it is with the plus charge. So it's going to come here and react with OH. And when it reacts with OH, it will want to form as what? Water. Now, check something. When it forms as water, what happens? It means now the concentration of OH will decrease. The concentration of OH will decrease, and the concentration of OH, when it decreases, Le Chatelier will say, let's now try to go to that side. Let's favor the forward reaction such that we will transfer some of the concentration of OH from this compound to the off. And then when we favor the forward reaction, the concentration of this one will decrease, the concentration of this one will decrease, and this one will now also increase. But initially, the disturbance was a decrease in concentration of OH minus to form water. Okay, so this one is Le Chatelier making its effect. So now let's reason. What will happen to the mass of the thing? The mass of that thing will decrease. The mass of calcium hydroxide will decrease. Why? when we use Le Chatelier, we will say, we'll tell the examiner that addition of HCl, okay, will now, okay, let me say, when HCl is added, the concentration of H plus from HCl will react with, okay, let me not say concentration, the H plus, okay, sorry, the H plus from HCl will react with OH minus to form water. And then when that happens, the concentration of OH minus will decrease. And when the concentration of that one decreases, and the forward reaction will be favored. Forward reaction will be favored. Okay. And we know when the forward reaction is favored, hence the mass of calcium hydroxide decreases. Okay. What's important here is you realizing that the H plus will decrease OH minus. Okay. The OH minus will decrease due to the presence of H plus forming as water. And then now the forward reaction will be favored. The forward reaction will be favored. Okay. Initially 70 grams of this one, initially 70 grams of that one is placed in a 3 decimeter cubed container at 250 degrees. The container is sealed and the reaction is allowed to reach equilibrium according to the reaction like that. Okay. The Kc values of the composition of this one is at different temperatures like that. As the temperature increases, what happens to the Kc? The Kc increase. So we know that the Kc increase if the forward reaction is favored. What do I mean? For Kc to increase, since well it's the concentration of products divided by concentration of reactants. For Kc to increase, we need the products to also increase. And for the products to increase, we need the forward reaction to be favored. So now it tells me that the forward reaction is favored, and I know an increase in temperature favors what? Increase in temperature favors endothermic reaction, by the way. So an increase in temperature favors endothermic reaction, and then the Kc increases, it means the forward reaction is favored. So it means now the forward reaction is favored, endothermic reaction is favored. So it means the forward reaction, it is endothermic, since well they're both favored. Okay. The question is the decomposition of NH blah 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 an exothermic or endothermic reaction? Well, the answer is endothermic. Why? You explain using the Chatelier's principle. When you explain using the Chatelier's principle, you're gonna tell us that increase in temperature favors endothermic reaction. And then you need to tell us that when Kc increase, you need to tell us that Kc increases when concentration of products increase. Okay? Therefore, for us to have the increase in products, therefore, forward traction will be favored. Forward traction will be favored. And now you know that when we favor the forward traction and an increase in temperature favors the endothermic reaction. Since well, they are both favored, it means now, therefore, it means the forward reaction is endothermic. I hope it makes sense. Now calculate the mass of NH4HS that will be present at equilibrium at 250 degrees Celsius. Okay. Well. Well, I know, okay, for me to draw this one, one thing that you need to note is that no solids or liquids are present at equilibrium. Or we do not include them at all. We do not include solids and all of that. But what we're gonna do, we're gonna say, okay, let us draw our RIC table quickly. I'm gonna just draw a quick RIC table. Okay. So let's say this is a ratio, and then this is initial mole measured in mole. This is a change in mole measured in moles. And then we have equilibrium moles measured in moles. And then we have equilibrium moles, we have equilibrium concentration, where we know that C is equal to number of moles at equilibrium divided by volume. And my volume is 3 decimeter cubed. So I can say, okay, let me do that quickly. Okay. Alrighty. Now, when I do that, I have what? Remember, I still say this. This one is not supposed to be at equilibrium. So this block, we don't necessarily need. But we're going to use it just for purpose. But we don't need this. I'm going to write this in red. So I'm going to scratch it out after using it, okay? And then here we just have NH3 plus H2S. So the ratio for all of these is 1:1:1. So the initial mole of NH4HS, we know. How do I know? Because we have the what? We have initial mass of 70 grams. So we have initial number of moles of NH4HS going to be equal to initial mass divided by molar mass, which now gives us initial mass is going to be 70, and then the molar mass of this one, when you do it, it is 51, and it will give us something like 1.373 moles. So you can put it here and say it is 1.373 moles. I'm gonna scratch this block because you don't need it, because why? It is a solid, guys. This is a gas. And then this one initially, NH3 and H2S initially they are zero because they are what? They are reactants. Okay, they are reactants. And then change. This one will decrease, this one will plus. Why? Because reactants get used up and products are formed. And then the change you did not know, we just say it is X for all of them. And then for this one, it's going to be just X, and then we'll have X divided by 3, X divided by 3. And then the equilibrium moles is going to be 1.373 minus X. So the question was, calculate the mass of this one that will be present at equilibrium. So I need to find the equilibrium moles before, okay? And then now Kc is going to be concentration of the products, which is what? Concentration of the products, which are my what? My products I have NH3 and then H2S. Do I divide by the concentration of reactants? No, because my reactant is solid. So I need to make you aware that NH4HS is a solid. And in Kc formula and Kc calculation, we only need aqueous solutions as well as gases. Okay, so, and also at 25 degrees, so not 25 degrees, at 250 degrees Celsius, my Kc it is 18 times 10 to the power of negative 2, which is 0.18. Concentration of this one, it is X divided by 3, X divided by 3, and then this will be 0.18 multiplied by 3 multiplied by 3, which is 9, and then you have X squared, and then you square, and then you see that the value of X is now 1.2. Now that I have this, I can say number of moles of NH4HS in equilibrium. It is 2. Not 2, 1.373 minus 1.273, which is just 0.1 moles. And then I'll say, therefore, number of moles is equal to mass over molar mass. And then the number of moles is going to be 0.1. The mass is unknown. And then molar mass is still 51. Therefore, the mass of NH4HS at equilibrium is going to be now 5.1 m's. And then I go back and say, oh, I do not need this block. I'm not supposed to include this block. So I'm going to just do this to the entire block, because now solids are not included in my calculation. Okay. It was just there to make me see how the changes occur thereof. Hence, I did not even bother to find concentration because I wasn't going to use it either way on the Kc calculation. Okay. So that is what we had for question 6. It was not bad. It was very beautiful. Just wanted you to know your theory very well. Okay, let's move on to question 7. 7.1, phosphoric acid is an example of an acid that can ionize in 3 steps, okay? Because it has 3 protons, okay? So it is triprotic, by the way. So it ionizes in the first step, second step, and third step, like that. So here they ask us, okay, which one between H2PO4 minus and HPO4 2 minus. Which one is a stronger acid between the two? Which one is a stronger acid between the two? So now the answer is very beautifully easy, and they say using referring to the data table like that. So we see that this one is the strongest one because it has a higher Ka value. Okay, you're going to say it is H2PO4 minus in aqueous. Minus is very important, very important. It has higher, has a bigger Ka value than, you can say than HPO4 2 minus. Well, that can be accepted. Write down the formula of a conjugate base of H2PO4. Well, for us to have a conjugate base of this one, it means this one needs to be an acid, okay, so that we have a conjugate base. And I'm not going to look at the graph, but we need to know that if this is an acid, remember an acid, it is a proton donor. So it needs to donate a proton so that it will be H. When it donates proton, it will be left with one proton. And then instead of minus, it will now be 2 minus. So the conjugate base is going to be HPO4 2 minus. And by the way, a conjugate base should be one proton less than my acid. And then the conjugate acid should be one proton more than the conjugate base. Okay. Then we are fine, just put aqueous. Identify a substance behaving as an ampholyte in directions. So let's look at these individual. So we know this is an acid, react with this. So this is a base, and then it forms, this is an acid, and then this is going to be a base. And then this one here, donate. Okay, so this is an acid here, and then this is a base. This is an acid, this is a base. And HPO4 donated again. So this is an acid here, this is a base, this is an acid here, this is a base. So already H2O no, H3O plus no, but when I look between H2PO4 minus and H2PO4 minus, it acts as a base in reaction 1 and acts as an acid in reaction 2. So you can say H2PO4 minus in aqueous, or there is another one. Another one, can you see that HPO4 minus? HPO4 2 minus acts as a base there. HPO4 2 minus acts as an acid in reaction 3. So you can say, or HPO4 2 minus. In aqueous, by the way, also. Okay. Sodium hydrogen sulfate is dissolved in water. When we dissolve this in water, when we dissolve that in water, it's going to form Na plus as well as HEO4 2 minus when it dissolves in water. And then this is just a spectator ion. This is just a spectator ion. Therefore, this will be our thingy. And then the question is our solution going to be basic or acidic? Well, it's going to be basic because it's going to form as OH minus. But now, let me show you why I'm saying it's basic. Yeah? Check. Since one spectator ion does not affect pH, we are going to take HPO4. And we'll make it react with water. And you know this has the capability of doing what? This is a what? This is a, it is short of what? It is short of hydrogens because of the 2 minus. And now it means it has the ability to accept. If it has the ability to accept, it means it will act as a base in this case. Then this one has the ability to donate. So it means this one will act as an acid. So It means if that's the case, this one will donate. Okay, when it donates one hydrogen, it's gonna have H instead of one. We now are gonna have two PO4. By the way, this is in aqueous. This is liquid. And then we have two hydrogens now, but now the charge will now move from two negative to negative one because we are now left with only one to complete the cycle. Okay, and then plus we took hydrogen from H2O to form us what? OH minus, which is also an aqueous solution. So yeah, can we see that? Okay, so yes. So now this is us trying to show that it's gonna produce OH minus. Hence now it is what? It is a acidic solution like that. Okay. Sorry. Cool. Cool, cool, cool. Now we can move on to 7.2.1 calculations now. Barium hydroxide is dissolved in water according to the balanced equation like that. Yes, yes, yes. And we see that for every 1 mole of barium hydroxide, it produces 2 moles of hydroxide ions. And then a 100 centimeter cubed solution is prepared by dissolving an unknown of barium hydroxide at 25 degrees Celsius. Out of the 100 centimeter cubed solution, 25 centimeter cubed of this barium hydroxide is reacted with 15 centimeter cubed of 0.2 mole per decimeter cubed of hydrochloric acid. Okay, so this one, it is the one that is in 25 centimeter cubed, and it reacts with what? HCl to form whatever that. And then the final pH of the solution, it is this much. Remember, pH is measured. Let me say pH measures the final solution. Okay, let me say we measure pH. Okay, we get pH from the contents left in the flask, or basically the one that are in excess. The one that is in excess that is going to remain in the flask is the one that will measure its pH, because it's the one that will tell us whether the solution is acidic or basic. So in this case, we can see that the final pH, it is this one. It is 12.62. So it tells you that the solution, it is basic. So it tells you that more concentration of hydroxide were present. Actually, concentration of hydroxide were present at the pH, at the final at the flask, at the completion of the reaction. So it means 7.2.1 in terms of final, calculate the final concentration of hydroxide ions in the flask. Well, we know that they are the ones that are present due to the pH. The pH, it is greater than 7, it is basic. So I can say, first and first, I can say pH plus POH, it is equal to 14. And then say pH, so the POH, it is equal to 14 minus 16 point, so not 16, 12.62, which gives me something like 1.38. And then I can say, okay, I want to find this one. POH is going to be negative log of OH minus. And by the way, the OH minus that we are checking here, it is the one that is in excess, that is the one that is left in the flask, okay? POH, it is 1.38. And then the concentration of OH minus, just take note, guys, it is the one that is in excess. It's going to be something like, you're going to say 10 to the power of negative 1.38. 10 to the power of negative 1.38, it is 0. Moles again. Or someone might say pH, it is equal to negative log of hydronium ions, and then used this 12.62 as it is to get negative log of hydronium ions like that. And then you get hydronium ions to be something like 2.39887 times 10 to the power of negative 13 mole. Not this. These are not moles. These are mole per decimeter cubed. Okay, mole per decimeter cubed, and say concentration of OH minus, okay, multiply by concentration of H3O plus. We are using autoionization constant 1 times 10 to the power of negative 14 at 25 degrees Celsius, by the way. It's very important that it is at 25 degrees Celsius. And then concentration of OH minus multiply by concentration of this one, which is 2.39887 times 10 to the power of negative 13, and then 1 times 10 to the power of negative 14. When you divide, you'll see that concentration of OH minus, which is the one that is in excess, 0.0147 mole per decimeter cubed. And then I can say, okay, let me find now 7.2.2. Find the number of barium hydroxide used in 100 centimeter cubed solution. Okay, what I can do is I can say, okay, I know that, well, first thing first, I can say, let me find the number of barium hydroxide that reacted, okay, that reacted with hydrochloric acids. So I'm going to say number of moles of hydrochloric acid is going to be equal to CV, where C it is now, okay, should I do it this in one step? Yes. Which is, concentration was, remember, concentration was 0.2. The volume was 0.015, which is 15 centimeter cubed, okay? You're going to divide that by 1,000. And then you get the number of moles of HCl to be something like 0.03. 0.003 rather, moles. And then according to the ratio, okay, according to the ratio, number of moles of barium hydroxide is half number of moles, because the ratio it is 1:2. So barium hydroxide is half of that of number of moles of HCl, which is half multiplied by 0.00. Okay, by the way, I need to indicate that this is number of moles of barium hydroxide that reacted. Okay, it's going to be 0.03, which is 0.0015 moles. Now I found the reacted. Now I need to find the ones that were in excess. Okay, how can I find those that were in excess? I know I'm gonna say the number of moles of hydroxide ions that were in excess. It is equal to CV, which is equal to concentration of the hydroxide. Sorry, yes, concentration of the one that is in excess. It is this one, 0.0147. But now the volume needs to be a sum of the volume. The sum of, remember, it is in this part here, and the volume that they added, it was 25 centimeter cubed, and they added it to the 15 centimeter cubed. So the volume that was found in excess is going to be 40. In excess, the volume is going to be 40. So you're going to use 40, which is 0.04, basically. And let me just confirm. Where's my calculator? 0. Okay. 40 times 10 to the power of negative 3. Yes, 0.04, it's fine. And then we get out, it is how much? It is something like, whew, not a beautiful number at all. Okay, I'll just use it as it is now. 0.001688 moles. And then I'm going to say, okay, number of moles of barium hydroxide. Therefore, it means that is in excess. And I know the ratio between barium hydroxide to hydroxide, it is 1:2. So it means it's going to be half. It's going to be half number of moles of hydroxide ions, which is just half of these. And it's going to yield to something like 0.0008. I think there are more zeros now. 0.00001668 divided by 2. Oh, okay. Moles. Now that I have number of moles of barium hydroxide in excess and number of moles of barium hydroxide that reacted, I can say number of moles of barium hydroxide initial. By the way, this is in 25 centimeter cubed. Just remember that. It's going to be this one, the reacted, plus the initial, the excess. Remember, when something is initial, when you remove the one that has reacted, you're left with the initial. So it means initial plus reacted, it's going to result to that. So I'm going to say 0.015 plus 0.000834, which is something like 0.002334 moles. Okay, now that I have number of moles that are initial in 25 centimeter cubed, I need to find that are initial in 100 centimeter cubed. So I need to say number of moles that are initial in, I know that number of moles of barium hydroxide in 25 centimeter cubed is going to be equal to number of moles of barium hydroxide in 100 centimeter cubed divide by 100 centimeter cubed multiply by the 25 centimeter cubed that we took. Basically, what we are saying is, we are saying 25 centimeter cubed of the initial 100 centimeter cubed number of moles gives us the number of moles that are in 25 centimeter cubed. And then when you substitute this to be, remember, you now know to be something like, this value, you know to be something like 0.002334. And then when you do your mathematics, you'll realize that the number of moles of barium hydroxide in 100 centimeter cubed, it's going to be equal to something like 0.0093934, I can say, moles, which is the same as 9.34 times 10 to the power of negative 3 moles. So yeah, guys, this is how I would have went about that question. Okay, finding the number of moles of this, and then using the ratio, and then finding the one that is in excess, and then using the ratio, and then adding them together. Okay, and then now this formula here and the answer, I think it is 1, 2, 3, 4, 5, 6, 7. The other mark, I think, should come from, let's see, Yeah, we can put it here. Okay, we can put it there. Or to one of the formulas, by the way, to one of the formulas. Okay, so that is that, guys. That is basically this was an interesting question of question seven by the way. Okay, let's move on now to question 8. Question 8, the diagram below represent a cell that operates initially under standard condition. Yo, people when they hear standard condition, they think of STP. No, standard conditions means now three things. Concentration of 1 mole per decimeter cubed in aqueous solutions. And then it means the temperature of 25 degrees Celsius or 298 Kelvin, or it means 1 atmospheric pressure, which is 101.3 kPa, but this one needs to be gases. So this is what we refer as standard conditions. Concentration of 1 decimeter cubed, 1 mole per decimeter cubed in aqueous solutions, temperature of 25 degrees Celsius or equivalent to 298 Kelvin. Also the 1 atmospheric pressure, which is 1.01 or 101 kPa or 1.01 times 10 to the power 5 Pa. But also only in gases, very, very important when we have gases. Okay. Apart from that, these two apply everywhere. But if there is no gas, this one does not apply. All right. First thing first, define what is an electrolyte. Okay. An electrolyte, it is what? We say it is a solution that conducts electricity through the movement of ions. So we know we have an electrolyte in here. We have an electrolyte in there. Okay, which ion concentration, Al3 plus or zinc 2 plus will increase? So you need to know which one will have a concentration that will increase. Now, when we check here and when we consult our table of reduction, we know that this one, zinc here will undergo. Okay, you can check it using your table 4B or table 4A, however which one that you use. Okay, when you use table 4B, just highlight this one and highlight this one. And after highlighting them, just do this between the two of them. And say this one at the top undergoes oxidation. And you're gonna write direction from this side going to that side. And this one at the bottom undergoes reduction. And you're gonna write it from here to there with one arrow. And then we get to see that this one, sorry, this one will be my anode. This one will be my anode. And this one, let me remove this. This one will be my cathode. And remember, cathode undergoes reduction, red cat. Anode undergoes oxidation. Remember the abbreviation red cat. Here an ox. Okay. Red cat, reduction, cathode, anode, oxidation. So if this one undergoes oxidation, it means aluminium will be oxidized to aluminium 3 plus. So you can say aluminium is going to be, okay, by the way, I'm just writing the half cells in case we're going to need them. Aluminium is going to be oxidized. And again, remember oxidation is increasing oxidation number. Also oxidation, it is what? Oxidation is loss, oil rig. Oxidation, it is loss, so it's going to be, how do I know it is this one? Because this is a pure aluminum and Al3 plus. Just make sure that you are aware of that. And then at the cathode here, I'm going to have this one will undergo reduction. So it means zinc 2 plus will undergo reduction, will be reduced to zinc solid. This is aluminum solid, aqueous. Zinc 2 plus aqueous. Okay, zinc 2 plus aqueous. Let me just do this. Okay, we are fine. I wanted to confirm something. Okay, and then now we can beautifully answer the questions, I guess. So the question was, which ions Al3 plus will increase? So this one. Why? You can say Al will undergo oxidation at anode. Okay, yes, Al will undergo oxidation at anode, or you can say Al3 plus is a stronger reducing agent than Zn2 plus. If you're a stronger reducing agent, it means you're going to cause the other one to undergo reduction, whereas when you go what? Oxidation. Okay. This was supposed to be Al. Okay. Write down the cell notation for this cell. Well, the cell notation, just know it is what? It is a anode. It starts with everything in the anode, salt bridge, everything in the cathode. But when we write it, it's going to be whatever in the anode. What is in an anode? It's this one. So it means an anode is going to start from aluminium moving to aluminium triplet. So it's going to be aluminium, which is in solid, moving to aluminium triplet, which is my aqueous solution. And then salt bridge, remember this tells me I'm changing a phase. And then cathode, I'm going to move from zinc 2 plus, which is still in aqueous Leona, salt bridge moving to zinc solid. Fine. Cool. Then the electrolyte in the aluminum half cell, or in the aluminum half cell, okay, is prepared by dissolving some aluminum sulfate. And by the way, aluminum sulfate can produce two aluminum ions. So can you see it has two? So it can produce two. So for every one aluminum sulfate half cell, there are two aluminum ions that are produced. So the question is, calculate the mass of aluminum sulfate needed to prepare 250 centimeter cubed of this solution so that the cell operates initially under standard condition. What do I know? I know that the concentration of aluminium 3 plus, which is an aqueous solution under standard condition. Remember, what did I say? We said it's going to have 1 mole per decimeter cubed concentration. Therefore, I know that for every 1 mole of this, there are 2 moles of that one produced. So I can say for every 1 mole of, so I'm going to say concentration of Al2SO4 3 is going to have half the concentration of, because for everyone there are 2 of those. So it means for every 2 of aluminum, there are 1. So it means for everything of this, there is half of aluminum. Okay, there is half. So aluminum, it is half of concentration of aluminum plus. So it's going to be half multiplied by 1, which is just 0.05. 0.5 mole per decimeter cubed. And then now that I have concentration of this one, I can find mass. How? Because I know that C is equal to mass mv. Still remember the formula? I believe so. And then the concentration, it is 0.5 The mass is what I'm looking for. The molar mass of this one, when you output it and do your mathematics and use your periodic table, it will be 342 multiplied by the volume. With the volume, it is 250, but in decimeter cubed, it is 0.25. And then the mass of my substance thereof, which is aluminum sulfate, it's going to be something like 42.75. 42.75 grams. So yes, guys. Standard condition is not, this is not equal to STP. This is not STP, guys. Standard condition is not STP. Okay. Yes, so let's move on to the last question of the paper. Question 9. Okay, the diagram below represents a cell used for the refining of copper. So if you are refining copper, it means we're gonna refine, or whatever that you're refining, we're gonna refine it at the cathode. So remember, these are negative, 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 and remember the cathode is negative in electrolytic cell, and this is gonna be my anode, positive. And then it means here we'll have impure. What are we trying to purify? Refine copper. So it means in here we'll have impure copper with whatever. And we are told that the unrefined copper contains zinc as the only impurities. So it means here we have impure copper, and impure copper has zinc. That will be our, okay, remember it is an anode. Also, the copper here will undergo oxidation ion, okay? So these are the impure, but we know that we want to refine what here? We want to refine copper. Okay, so it means here we will have copper deposits. Copper deposits. Copper deposits here. We will have copper deposits here. So it means the mass of an electrode Q will increase, whereas the mass of electrode R will do what? Will decrease. Okay, this one will increase, this one will decrease. So now let's check exactly what happens. Is this an electrolytic or a galvanic cell? We know, guys. Question 9, it's an electrolytic cell. Electrolytic cell. How do I know? Happy, I see an electricity component here, electrical component. And they tell us that when the switch is closed, it is found that after T hours it is found after T hours that the amount of Cu2 plus ions in the electrode in the electrolyte changed by. So the amount of Cu in here in the electrolyte changed by Cu2 plus. Okay, remember we have zinc 2 plus in here floating around. So they changed by 0.05. So it means there was an increase by 0.05 in the electrolyte. Okay, but where do they come from? They come from the what? They come from the anode here. They come from the anode here. They come from the anode there. They come from both of these. But which one? We will see. And then another thing happened that we are told is that, and 0.15 moles of copper were deposited on electrode Q. Okay, so if 0.15 mole of copper was deposited in here, and remember it was formed from this anode, okay? It was formed from the ions from this one. And so it means now, one of the 0.15 there came from copper. So it means copper 2 plus. It means copper 2 plus, okay? Let me just confirm something. Mm-hmm. Just a bit. Okay. Okay. So now we have copper 2 plus here uh, that was that combined with an electrode again to form now my copper. So I know this is 0.15. Okay. This is 0.15. Okay. And then let me just check the statement again. The amount of Cu2 plus ions in the electrolyte changed by 0.15. In the electrolyte changed by 0.05. So it means now, it means now if this one changed by 0.015, it means now, okay, I want you to make sense of this one. I want you to make sense of this part that I'm gonna say here. Okay, if 0.05 were found in the electrolyte here, and 0.15 of copper was deposited in here, it means somewhere, somehow, there is what? There is 0.1 mole of something that was deposited. Which one is that something? So, which one is that something? Check now. We will have something like this. We will have copper, it is 0.15 that was deposited in there. And this one, it is Cu2 plus. Cu2 plus we know to have increased by 0.05. Okay? Therefore, there is something that is left there. What is it that is left? What is left, it is 0.1 mole. So this 0.1 mole will come from where? This 0.1 mole will come rather from what? From the zinc. So this 0.1 mole will come from the zinc because already copper was 0.15 of it, and then copper 2 plus was 0.15. Okay, so they took 0.15 of this and they deposited there here. Okay, so it means there was 0.05 of that one. So it means the other 0.1 came from, so it means 0.1 came from zinc 2 plus. Okay, so it came from zinc 2 plus. Let me just put it here, 0.1. And then this is now fairly easy because now it means on this anode, okay, there was a decrease in concentration of what? There was a decrease in number of moles of copper 2 plus by 0.05, also a decrease. Remember, a decrease in an anode is going to cause an increase in the electrolyte because as they are lost in here, they go to the electrolyte and go to the cathode. And there was a decrease also in the number of moles of zinc 2 plus, which is how much? Which is 0.1. And by the way, we know as per reaction is that copper and copper 2 plus are in a ratio of 1:1. Zinc and zinc 2 plus are in a ratio of 1:1. So yeah, we'll go to that question when it is time. So how will the concentration of zinc ions in the electrolyte be affected during the refining of copper? Okay, so we just saw that it is 0.1, by the way. It will increase, but now we need a suitable reason. Even though they did not want it, I'll give you. Why is it going to increase? Because zinc will be oxidized to zinc 2 plus. This is your answer. Okay, zinc has a stronger reducing ability than copper. Okay, zinc has a stronger reducing ability than copper. Hence now, remember, if you have a stronger reducing ability, it means you will cause the other one to undergo reduction, whereas when you go what? Oxidation. So it means zinc will undergo oxidation. Okay, yes. And now the question is, will the amount of copper ions increase or decrease? Well, they will decrease since, well, they are forming the copper here. Okay, This copper 2, sorry. This concentration of copper 2 plus will decrease because they are used here to form what? Copper plus. So they will decrease. Decrease. I will also write decrease. And now we need to use the relative strength of oxidizing agent present to a reason for that. So we will say copper 2 plus is a stronger oxidizing agent than what? Than zinc 2 plus. Thus, if you're a stronger oxidizing agent, it means you'll cause the other one to undergo oxidization, whereas when you undergo what? Reduction. So it means thus Cu2 plus will be reduced to copper at the anode. Okay. So now hence it will decrease. It is a stronger reducing agent than this one, and it will be reduced. Okay. Interesting question. But we have already analyzed this question to say now number of moles of zinc 2 plus are gonna be 0.15 minus the 0.05. Remember this one, it is from copper. Okay. And then this copper deposit is 0.15. Then this is the 0.05. So it will be something like 0.1. So I can say now first thing first, when I want the change in mass, I'll say, let me calculate the number of moles that were lost in R. So I'm going to say number of moles of Zn2 plus in R is going to be 0.15 minus 0.05, which is just basically 0.1 what moles. All right. So, and we also have now number of moles of copper 2 plus from R that were present in an electrolyte. Remember, we take them from the anode. We took them from the anode here. We took them here before they were present. We lost them in the anode before we gained them in the electrolyte. So it is 0.05. Okay. But remember, okay, this is moles. But remember, number of moles of Zn2 plus is equal to number of moles of Zn in R. So it's very important that you take note of that, which is 0.1. Also, the number of moles of Cu2 plus in R, it is equal to number of moles of Cu in R, which is 0.05 moles. So therefore, how can I calculate the change in mass? Okay, the change in mass. So the change in mass at R is gonna be change in mass. Okay, let me do this. It's gonna be equal to change in mass of copper plus the change in mass of zinc. So let's just do that. Mass of zinc is gonna be number of moles is equal to mass right by molar mass, which is just zinc. It is how much? 0.05. Mass is gonna be what I'm looking for. Molar mass of zinc. Molar mass of zinc, it is 65. We all know that. And then mass of zinc. Okay, let me say lost at R. Okay, lost at R. It's gonna be something like 0.25 grams. And then let's also do the same for our copper. Mass of copper at R divided by molar mass, which is 0.1. This is equal to the mass of copper at R divided by molar mass, which is 63.5. And then mass of copper at R, it is something like 6.35 grams. Therefore, change in mass at R is going to be the combination of these two. Grams plus 6.35 grams. And then we see it is something like 9.6 grams. Okay. So this is what it is. So it is what it is. It is what it is. So yes, this was the one of the interesting 6 marks question that you can encounter. It was a little bit challenging. I understand. So yeah, this is the total of 150. Hopefully, everyone who was writing this paper did well, and those who are practicing using this paper for 2026 and all the upcoming years, you found this paper very helpful for your studies again. So thank you very much.